Hello everyone, my name is Jian. I'm from the University of Michigan. Today I'm going to present the work on the deep UV-assisted capacitance-voltage characterization of post-deposition annealed aluminum oxide on 001 beta-gallium oxide MOSCAPs. Gallium oxide is a very promising material for high-power applications due to its ultra-wide bandgap, high breakdown field, high polygraphic of merit, the availability of the mild growth of box substrate, and fan engineering. High quality of gate dielectrics are very important for MOSFETs and MOSFETs. There are several key metrics for dielectrics such as high dielectric constant, large band offset, interface state density, and Bach trap density. Specifically, for the interface state density, this results in the variation in the gate modulation, channel mobility, and current collapse. The defects in poor dielectrics with high Bach trap density leads to a leakage path and failure to achieve high critical breakdown field. So it's very necessary to characterize interface state density and Bach trap density. There are several conventional characterization ways for it. However, they may be limited to probing the interface state profile over the whole bandgap of gallium oxide due to the long emission time of traps near valence band. Recently, the deep UV-assisted CV technique is developed as an alternative technique to extract interface state for wide bandgap semiconductors. This technique utilizes deep UV illumination during depletion bias to make sure all the traps are ionized and can be extracted from the following CV measurement. Using this method, several groups have characterized the interface states in aluminum oxide on -201 gallium oxide. And for the other orientation, there are also previous results on it using conventional characterization methods. However, there is no information of Bach trap and no information of the MOSCAP in 001 gallium oxide orientation, despite of some most successful gallium oxide-based power devices are fabricated in this orientation. So our work will be focusing on the 001 orientation. We choose HF as our surface pretreatment is because compared to piranha solution, we notice the HF doesn't change the surface morphology and there's little increase in the surface roughness. Our aluminum oxide dielectric is deposited in ALD using TMA and water as precursors. The figure here shows the CV hysteresis measurement of 3 samples with different ALD deposition temperature of 150, 250, and 300 degrees C. We can see less hysteresis and higher dielectric constants were measured as deposition temperature increases. And the lag is observed here in the CV curves with lower ALD deposition temperature of 150 and 250 degrees C. This is attributed to the Bach trap occupying at a certain energy level. The figure on the left shows the effect of the post-deposition annealing condition. The black curve is without post-deposition annealing, and the blue curve is the PDA in nitrogen, red curve is PDA in oxygen. We can see PDA in both nitrogen or oxygen improve the dielectric quality. And the dielectric constant of 8.7 and less hysteresis is achieved in PDA in oxygen. The remaining hysteresis is associated with the continuous interface state. We also characterize the forward breakdown. of the MOSCAPs. Here we can see when we increase the deposition temperature of ALD, the breakdown voltage also increases. And the figure on the right shows that compared to the sample without PDA, which is the red curve, the breakdown voltage increases when annealed in oxygen but decreases when annealed in oxygen. It can be explained by the oxygen vacancies in the aluminum oxide field. So annealing in oxygen kind of reduces the oxygen vacancy in the dielectric field. Here is the deep UV characteristics of MOSCAPs. The ideal dark curve, as shown in the short dashed line, was shifted here to the solid black line to match the capacitance value of post-deep UV curve in the deep depletion regime. The delta V here is the voltage between the ideal dark curve and post-UV curve for a given capacitance. This is associated with the interface state and the bulk trap. Using that delta V, we can get the dt over the whole energy scale. And here are the three figures of the dt as a function of energy with the different aluminum oxide thickness of 15 nanometer, 32 nanometer, and 45 nanometer. The dt is the function of the interface state, the thickness of dielectric, and also bulk trap. As you can observe, there is the energy peak shown around the energy of 0.5 electron volt. And this can be attributed to the energy band barrier shown here at the interface between the aluminum oxide and gallium oxide. This band barrier can accumulate the generated holes. So in previous research, if there's no band barrier between the silicon nitride and gallium nitride, the extracted DIT curve is very flat. But if the dielectric create the band barrier, they also observe the peak here. So to calculate the average DT, we remove this peak and then get the average DT for each thickness of aluminum oxide. Then we plot the dt as the function of thickness. From this physical equation, we can see the intercept is the interface state, and then we extract the slope, which is tied to the bulk trap. Our interface state is around 1 × 10⁻², which is relatively larger than the other orientations. So previous research has shown that the formation of the crystalline aluminum oxide interlayer between dielectric and gallium oxide helped reduce the interface state. It is very important to note that 001 is a very strong cleavage plane with less surface adhesion energy. So there's less possibility of crystalline aluminum oxide formation on 001 orientation, which lead to kind of larger interface states. In summary, we have investigated the interface state and dielectric bulk trap in aluminum oxide on beta gallium oxide 001 MOSCAPs through CV hysteresis and deep UV assisted CV measurement. We also studied the effect of deposition temperature of ALD and post-deposition annealing conditions. We get the interface state from the 001 orientation, which is a little bit larger than the other orientation, and it can be attributed to the less possibility of crystalline aluminum oxide formation on the cleavage plane. Thank you so much for the listening. See you soon in the post session 2.